Okay.
Welcome.
Whatever she's fine.
There's just so much stuff, like so much more stuff to do this year than last year. All right, so today we're gonna go over the assignment that's up there. There are some more questions than normal, but this section is maybe a little bit more a little bit more difficult than the other sections, and so we're not gonna do the what's it called? I keep saying we're not gonna do the constructive response. Yes, because it had some pretty difficult, in-depth math questions, which we're not going to do. So everybody close your Chromebooks. I have assigned the reading. The reading is, I don't know what all that is. I guess that should just be an apostrophe, but it turned into something different. It's Kepler's first law of planetary motion. And they actually go through all of Kepler's laws of planetary motion. Close your Chromebook. Don't make me tell you again. Kepler's law of first motion is the reading for today. Let me go ahead and open that up. And then we have the assignment pulled up right next to it so we can actually look at some of the questions. I think I went through most of the questions earlier and they're not too bad. So I was thinking about redoing the assignment and maybe taking some of them out, but I decided not to do that. I think maybe last year they had some more difficult questions in it, but this year it's not too bad. The constructive response was pretty difficult, so we're not going to do that. We're going to go through Kepler's 3 laws of planetary motions. We're going to talk about satellites, which are essentially moons, and we're going to talk about a couple other things. After we get done talking, the assignment shouldn't be too difficult. So Kepler was an early astronomer. He was a mathematician and astronomer in the early 17th century. He published 3 laws describing planetary motion. These 3 laws still stand today. And so way back in the 17th century, he did a lot of very detailed work. He used precise instruments. He took a whole bunch of measurements over and over and over again, and he was able to describe these laws, and they really stood the test of time. So we're still using them today to describe how planets move around. So his first law of planetary motion, I believe, I don't know that they're really laying these out super clear. This first law of planetary motion is that the planet's orbits are not circular but elliptical. And this is very important. For the most part, they're not like really exaggerated ellipses. I'm not going to bring the computer over, but they're not like a super big oval. They're really close to like a circle, but it's not a perfect circle. And that is important because as you watch the planets move through the sky, if you're taking super detailed readings, you will see that some of the planets during some of the years speed up. They actually go faster, and then they will slow down. And the reason for that is if you have, let me come back over here, and I guess this time I will bring the computer. I'm going to exaggerate this, but here's the sun. And here's your planet. And let's say, this is very exaggerated to prove the point, but let's say that is your orbit around the sun. So you have the sun here, and you have your planet orbiting the sun in an ellipse. So it's not a perfect circle. It's more like an oval, but not like an egg oval. It's not that exaggerated. But I exaggerated this for the purposes of showing you. If the planet's headed this way, it's headed towards the sun. It's feeling the sun's gravity pull on it more, and it's pulling in the same direction that it's going. And so the planets are going to speed up through this section. And they're going to be going their fastest right as they get closest to the sun. Then as they turn that corner and they head back out further away, the sun is pulling them back in the opposite direction. And so they're going to be slowing down in this section, and they're going to be going their slowest at that point. And so he noticed that the stars, sorry, not the stars. I got a telegram stuck in my throat. Sorry. I need a sip of water.
All right, evacuate.
Yeah, I'd say
Not like
that
a whole
too.
one. Was it good?
Was it worth it?
Oh yeah, totally worth it. I do it again. Wait,
That's all that matters.
10 times out of 10.
falls over.
The people at home are like, dang, Mr. Bailey almost died from a 10 grand. Yes, we use this effect to speed up our spaceships. Yeah, this is a slingshot effect. This is also this orbit is more like what a comet would undergo more than a planet, but I made this kind of exaggerated to show you what the planets. So Kepler noticed in his measurements and in Tycho Brahe's measurements that the planets would speed up during certain parts of the year and they would slow down during other parts of the year as they moved through space. And so he concluded that they were elliptical orbits and not perfectly circular orbits. So they talk about that a little bit here. We're not going to go through all the details, but if they ask questions during the assignment, you can come back and read through this. Now we get to Kepler's second law of planetary motion. So the second law states there's an imaginary line joining the planet to the sun that sweeps out equal areas in equal amounts of time as the planet travels around the ellipse of orbit. So let me come back over here and I'll give you a small example because I don't even have to draw it. Right here. Is this going to open up? This picture is going to open up in who knows how many seconds. It shouldn't take that long. And what they're going to see, here we go, is that if you take a specific amount of time, they have hours here. I don't know why they have hours. It should be like months out of the year. But let's say that you have, 13 hours? This is weird. I don't know why they put hours here. But anyways, each one of these different time periods is an hour. And you notice that when the planet gets faster and faster as it's going towards the sun, you travel more space in an hour, right? And then as you get slower and slower going away from the sun, you travel less and less space in your hour, but you're further away. And so Kepler's second law is basically like a math law that if you draw these lines in equal time periods and you take the area of that shape that it creates, all of these areas are equal. These look skinnier, and they are, but they're also longer. And so there's more area in there. And so these are short and stubby, these are long and skinny, but each one of these has an equal amount of area that it covers. This doesn't really apply much to space travel, or it's not important to know how the planets do this, but it is like a mathematical equation that he discovered, and it happens to be true for bodies moving through space. Now, can I go back? Is it going back? It shouldn't take this long. All right, so that's Kepler's second law of planetary motion. And if we go down a little bit, we get to Kepler's third law. Where are we at here? Come on. Second law. Third law. So Kepler's third law is the square of a planet's orbital period is directly proportional to the cube of its average distance from the sun. That's a little bit of math speak, but basically what they're saying is the further it is from the sun, the faster, or the slower, it will go around the sun. So these planets out here, like Pluto, even though it's not a planet, it's a dwarf planet, Neptune, Uranus, Jupiter, and Saturn, they take a long time to go around the sun because they're further away. So for Jupiter, it is 12 years to go around the sun. For Saturn, it's 29 years. For Uranus, it is 84 years. For Neptune, 165. And then Pluto way out there is 248 Earth years to go around the sun once. Where when you go in and you get closer, it gets shorter and shorter and shorter. Mars is 687 days, just about 2 Earth years. Earth is obviously 365 days. Venus is, where are we at? 225 days, so less than an Earth year. And then Mercury goes around the sun every 88 days. So once every 3 months, which is pretty quick. So the closer you are to the sun, the faster you're going to be going around. The further away you are from the sun, the slower you're going to be going around.
So what year is Mercury in right now?
That it depends on, are you talking about Earth years or Mercury years? And what year is it in? Like Mercury years? From the beginning of time, we don't know. Or from the beginning of the solar system, there's not really a calendar for Mercury. I don't know. Yeah, would you be starting from like the birth of Christ? That's a weird place to start for Mercury. They don't know nothing about that. So
What do you mean, hey?
there's no religion on Mercury.
He said there's no religion on
Yeah, they don't practice. They don't go to church every Sunday. So we're gonna move on to the law of gravitation. We've talked about gravity a little bit. Basically, I think what they want to go over, and I think this was one of the questions that we had a little trouble with last year, and I was looking to see if I needed to get rid of it. Gravity is based on two things. The mass of the object, so obviously a smaller object is going to have less mass and less gravity. A larger object is going to have more mass and more gravity. We talked about the bigger planets. We could never even go there because the gravity is so much that it would just crush our soft little puny earthling bodies. Where you go to Mars or the moon, where Mars has like a third of our gravity and the moon has like a sixth, we can leap around and hit golf balls like 500, 600 yards easily, even in a spacesuit, because there's just way less gravity and there's less air pushing around.
2,000 pounds on the moon.
Yeah, you probably could. Now it wouldn't weigh 2,000 pounds because you have less gravity. But yeah, you could lift a lot more mass on the moon than you could here on Earth. In the same way, have you ever been to the lake and picked up a big rock underwater? And you can pick up a huge rock underwater, but as soon as you get it above water, it gets a lot heavier because the water's not displacing it; it's helping affect the weight of it. You could pick it up on the moon, but when you get back to Earth, if you tried to lift it out of the spaceship, you're not going to be able to lift it out. And so, yeah, the size of the planet affects it. Also, the distance of the two planets apart, or the distance you are from the planet, affects your gravity. So here on Earth, you can go up in an airplane, and you can be traveling in the airplane, and you don't feel. I mean, you do feel the gravity, like you're still stuck to your seat, right? But if you go up high enough and you're in the International Space Station and going really fast, do they feel Earth's gravity? No, they're still held by it because the space station isn't just shooting off into space, but there's a lot less gravity there to feel, and they're not going to have the same effects because they're much further away than an airplane is. And so there's some mathematical equations that go in with these. I don't think there's any questions in the assignment today, so we're not going to spend a bunch of time on it. But here is the equation. Force is equal to gravity. You have your mass of one thing and your mass of the other thing. So if you're talking about the gravity between the Earth and the moon, you take the masses of both of those, and then you have the distance between them, the radius between them, squared. So that's the force there. Now let's see. They go through a couple problems. Sample problem. We're not going to do the sample problem. Rotation. They talk about rotation, the Earth rotating on its axis. One of the questions deals with the moon. I mentioned that the moon that you see in the sky, you always only see one side, right? So you don't ever get to see the backside of the moon because as the moon goes around the Earth, it's always facing the same direction towards Earth. It doesn't really rotate like the Earth does. Yeah. The moon, technically, depending on how you think about it in physics, it does rotate, but it rotates at the same speed that it orbits the Earth. And so it is kind of spinning, but it's spinning where it's always looking at us as it goes around. Does that make sense? So like if it wasn't spinning at all, as it went around on one side of the month, we would see one side, and on the other side of the month, we would see the other side of the moon. But it's kind of spinning at the same rate that it's rotating. And so what that's called is tidally locked. So you know the tides? The tides here on Earth are based off the pull of the moon and the pull of the sun. It's actually both of them. And so you can have high tide when both the moon and the sun are pulling in the same direction. And you can have like middling tides when they're opposite and low tides when they're pulling away from you in the same direction. But the moon, if there were water on the moon, the Earth would not affect the moon's tides. It's tidally locked. And so the Earth would always be pulling in the same direction because the moon doesn't really rotate relative to us.
So if there was water on the moon, it would only be on one side?
Not that it would only be on one side, but you wouldn't really have tidal waves and the water going in and out of little bays because the Earth is pulling on it in different directions, which is what happens. If you ever been at the beach for a long time, during just one day because the moon is moving around. You can put your beach chair in the sand right next to the water, and depending on whether the tide's going in or out, the water either gets further away or it comes in, and now all of a sudden your chair is like halfway underwater. What are you gonna say?
Oh, so you know the moon and whatever
Yeah.
controls our tides. On other planets, does it control like their dust clouds?
Maybe there might be some effect on atmosphere. It's probably a lot less because the particles are so much smaller. There's just not a lot to pull at there. But yes, you could have some tidal effects from moons in the atmosphere probably. Close your Chromebook. I know you already did your assignment, but that'll make you get off on the lecture. Yes.
Do you think that if we had 2 moons, our water would be going everywhere?
Yes, we'd have more complex tides for sure. Yeah. The tides would be more complex. We might still be able to figure it out. But because the tides are based on the moon and the sun, you can look up what the tidal heights will be for like years and years and years in advance. So if we were like a port town, we would all be much more familiar with the tides, and you can get in a book for like 2025 and know what day the super high tide will be and what day the super low tide will be.
If the moons were
Because we
lined
know
up,
where they're
would it
going.
pull more?
Yes, which is why our highest tide is when the moon and the sun are lined up in the same direction. They pull the water even more that way.
So if we had 2 moons lined up around the sun, it would just be like.
Yeah, it would be even more. Yeah, it would just be added on to each other. So they talk about that a little bit with Earth's tides and how it revolves in the sun. Do we have anything else? Oh, perihelion and aphelion. So this again is exaggerated, but imagine that we don't orbit the sun in a perfect circle. We're in this oval shape, this ellipse. There are 2 different points that you want to be aware of: that aphelion and the perihelion. And basically think of the aphelion, or I use the ph, as like the apex. Apex is like the highest point. So aphelion is going to be your furthest point away from the sun. Perihelion is your closest point to the sun. Also know that we do get further away and closer to the sun. That has absolutely nothing to do with our weather or temperature. The distances are so great that it's not like we're that much closer to the sun that it gets hotter. Our seasons, the way the Earth is tilted, more affects our temperature than anything else. But yeah, there's points in time in the year where we are much closer to the sun than other points in time, or relatively closer, maybe not much closer. Then they get into the equinox and the solstice. Equinox is like which term? Equal, yeah. Equator's not bad. But equal, and actually it is kind of like the equator, because in the equinox, the sun is perpendicular over the equator, and the day and night is the same amount of time. You have 12 hours a day, 12 hours a night. Those are the equinox. So we have 2 periods of those. There's summer, or I think it's summer equinox, and or maybe I'm wrong. No.
There's one in March.
So, yeah, I'm thinking of the solstice. Maybe there's only... No, there are 2 equinoxes. There's vernal and... Does it say on here? Yeah, autumnal equinox. Yeah. Autumnal equinox and vernal equinox, which is the spring one. Obviously, autumnal is autumn. And so that is the point in time where the days are 12 hours and 12 hours nights, equal. Then you have your solstices, like you mentioned. That marks the point where the sun reaches its highest point in the sky. So you have your winter solstice and your summer solstice. And that is going to be where either your days are the longest or your days are the shortest. Depends on what point, what part of the earth that you're in. So in Texas, we're in the northern hemisphere. So summertime, we get the longest part of the days, which is also the hottest because the sun is more perpendicular to us here at these latitudes. And so we just get it both ways. It's super hot and the days are super long.
You know what's crazy?
Yes.
We can see the sun, but we can't see those other planets.
Can we start now?
You can see the other planets at night, and you could see them at day if you had the right telescope, but you have to have a filter. The sun's just too bright.
Yeah.
Uh,
Telescope to see them at night.
No, you can see planets. You can't really tell that they're planets. Some of them just look like stars, But you can. I'd encourage all y'all, because it's free, download this app. Hold on, I'll tell you about it in just a second. What is the app? Sky Safari. And you can hold your phone and it will show you what you're looking at. So you can find like Venus, you can see Jupiter sometimes, you can see Mars. Don't do it just now. I'll write it on the board and you can do it in a second. Then they talk about the phases of the moon. I know I've been going over a lot, but they're going to ask about all these, I think. Do they show you the phases of the moon? Here we go. We'll open this up. And you can go ahead and open up your Chromebooks and start, because I want y'all to be able to get through these. Well, they don't even show you. So no, which one is the full moon? It's E. What do we call when it's the opposite of the full moon? New moon. It's called a new moon. And then we also have waning and waxing moon. Yeah, gibbous and crescents. Well, but there's waning crescent and waning gibbous and waxing crescent and waxing gibbous that kind of go around. So know those terms because they're going to ask you one. They're going to ask you which one is not one of the real terms. This is 17 questions, so if you don't get finished in class today, I do have it open through the end of the day tomorrow. Try to work on it for homework if you don't get finished, but if you do get finished, good.
What's number 1?
What's the question asked?
When a satellite always keeps the same side toward the
Oh, that's what the moon does. So when they're talking about satellites, they mean like moons around the planet, anything that orbits something. So the moon, no. The moon is always facing towards us. So there you go. Yes. Yes.
What's the farthest? Is it equinox?
No. Wait, you're talking about this thing?
It's the apex one.
Yeah, it's the one that starts with like the apex, so it's aphelion. Or aphelion. Aphelion. Yeah. Remember to open up the reading and be going up and down in the reading. That will help you out. If you have any questions, people at home, I know there's a lot of questions on this, but send me an email and I will get you helped out. But I did assign the reading, so you should be able to go in there and find your different answers. Thank you. Have a nice day.